Hello everybody, let us now discuss in this video about the effect of temperature on pendulum clocks. In the pendulum clocks, we will have a pendulum in which actually a metallic bob is attached to the clock, which is we're using a metallic sort of a wire or a bar, we can consider, or bar only, we take it as metallic bar attached with a bob. So now we know very clearly that time period of the pendulum, simple pendulum or pendulum clock, generally time period of a pendulum clock is equal to 2 pi into root over L by G. For the case where G is a constant and the length L is the length of the pendulum. This is the relation that we know in case of the time period of oscillations of a pendulum. Now, as we know, the length L depends on the temperature. So what we can say is, due to the rise of temperature, the length increases, and due to the drop in the temperature, length decreases. Means expansion on raising the temperature, the length of the solid increases, and on decreasing the temperature, the length of the solid or the length will decrease. In one case it will increase, the other case it will decrease. Now here in this case, let me assume a situation where the pendulum clock reach correct time when its length is L0. For the L0 length, it is reading the correct time. So by this we can write its time period. So its time period will be, yes, its time period can be given by this relation. I take it as T0 is equal to 2 pi into root over L0 by G. This is the time period. I'll assume this equation as equation number 1. Now the second point here is that I raised the temperature. So the temperature is raised by delta T. The temperature is raised by delta T. Now the new time period will be how much? The new time period becomes, I consider it as T, which is equal to 2 pi into root over L by G. Here this L is the new length, the length of the wire after a raise of delta T in temperature, and T is the corresponding time period, and here is the corresponding small t is the corresponding time period. Now let me assume this is equation number 2. This is equation number 2. Now from these equations above, from the above equations, what I'll do is I'll divide both of them. I'll divide the equations. Dividing equation 2 by equation 1, what will we get if I divide? See, once if I divide these, I'll get a relation like this, which is T by T0, T divided by T0 is equal to 2 pi into root over L by G whole divided by 2 pi into root over L naught by G, from which we can have 2 pi, and the G value also get cancelled out under the root, whatever G value is, will get cancelled out, and we can rewrite this relation as T by T naught is equal to root of L by L naught. Now this is equation number 3. Now, since this case where we have the rise in temperature, what happens since by this thermal expansion of by this relation of L is equal to, since you can take it as L is equal to L naught into 1 plus alpha into delta T. Here alpha is the coefficient of linear expansion, and from which further L by L naught can be written as 1 plus alpha delta T. So hence from the equation above, what will I get? Hence from the equation 3, we get, what will we get from the equation 3? Here, if you consider the equation number 3 and substitute this L by L naught value there in that equation above, I can rewrite the equation as T by T naught is equal to 1 plus alpha delta T under the root. So I just take the power and root as 1 by 2. Now, if you look at this equation here, we have T by T naught is equal to 1 plus alpha delta T. Now, for the condition taken for small values of alpha into delta T, for small alpha delta T values, we have 1 plus alpha delta T whole power 1 by 2 can be approximately equated to 1 plus 1 by 2 into alpha delta T. How do you get this relation here? Is very simple. This relation is by binomial expansion. That is 1 plus x whole power n is equal to 1 plus n into x for x very small compared to 1. For x value very small compared to 1. On that condition, we can arrive it at, here in the place of x we have alpha delta T, in the place of n we have 1 by 2. So it just can be written as 1 plus 1 by 2 into alpha delta T. So from this equation further I can write it as T by T naught is equal to 1 plus 1 by 2 times of alpha delta T, and from which I can write it as T by T naught minus 1 is equal to 1 by 2 alpha delta T. So further I can write it as T minus T naught divided by T naught is equal to 1 by 2 alpha delta T. So T minus T naught here is what we can take it as the change in the time period. Final time period minus initial. That will be delta T divided by T naught is equal to 1 by 2 times of alpha delta T. This here will give you the fractional loss in time. Fractional loss in time, or we can also consider it to be fractional gain in time as well. Now also we know very clearly that number of seconds in a day, we know that number of seconds a day has number of seconds in a day is 86,400 seconds. So what we can write is, so time lost or gained, I just time lost or gain also you can take, I just lost or gain per day is delta T is equal to 1 by 2 times of alpha delta T. The T naught goes the other side, and the T naught is per day calculation of time, and that T naught is how much here, into 86,400 seconds. Hope you understood how to calculate the loss or gain in the time due to the rise of temperature in the case of a rise or drop in the temperature in case of a in case of a pendulum clock. Thank you.